Let's talk about method of moments. We have worked with only a small number of probability distributions here, but there are many probability distributions that you could have worked with. Among the distributions that we have talked about, how many parameters do you need in order to characterize completely a normal probability distribution? Just two, okay? The mean and the variance. How many parameters do you need to know in order to characterize a chi-square distribution? Just one. If you know the degrees of freedom, you know what the thing looks like. How many parameters do you need to know in order to characterize a Poisson? Just one. How many parameters do you need to know in order to characterize a uniform distribution? Two. Meaning the lower bound and the upper bound on the interval that it's distributed on. So depending on the distribution, there may be many different parameters that determine or characterize it. The idea behind the method of moments is that the parameters that characterize the distribution will be functions of the central moments of the distribution. So for example, in the normal distribution, of course, the sample mean is the first sample central moment, and the population mean is also a central moment. The population variance is the centered second moment, but you can construct it from the first central moment and the second central moment. So if you let M stand for the moment, the population variance is M2 minus the square of M1. So knowing that, we could figure out the sample moments and work backwards to get the population parameters. So that's the whole idea behind method of moments, is to know something about the relationship between the parameters that describe the distribution and the population moment. We then use the sample moments to estimate the population moments and then solve for the unknown population parameters. So it's probably best to think about some examples. So as I already mentioned, the mean and variance are functions of the first two central moments. So the variance, sigma squared, is just the second moment minus the square of the first moment. And the mean, of course, is just the first moment. Suppose we had a uniform distribution. So we say that x is continuous, is a uniform continuous random variable on the interval a, b. And we wish to estimate the two parameters a and b, the lower bound and the upper bound on this uniform probability distribution. And one of the things that we know is that the mean is the integral from little a to little b of x times the density over the domain, or support of the probability distribution. We also know that the variance, sigma squared, is a function of the two parameters that define the distribution. So we can do the two integrals, and then we can solve for mu and sigma squared, the mean and the variance of this uniform random variable. So our method of moments estimators for the mean and variance would be to compute the sample mean and the sample variance and set those equal to the functions of the parameters. So we have two equations and two unknowns. So in this specific example, I said that the sample mean was 5 and the sample variance was 2.5. So 5 as a sample statistic should be equal to b plus a over 2. And 2.5 should be equal to b minus a quantity squared over 12. So you got two equations and two unknowns, and you can solve them. And so that would be our method of moments technique for estimating the parameters a and b. As another example, we could look at the inverse Gaussian. The inverse Gaussian has two parameters, mu and lambda. And we use the inverse Gaussian to model things like the transition from unemployment to finding a job. How long are people going to stay on the unemployment rolls kind of job? In economics, that's where we're using. I'm sure that in other disciplines, they use the same kind of thing. The inverse Gaussian is related to hazard models, for example. And you use hazard models to model the time to default on a bond. So there are whole classes of models that use this kind of distribution. So we're going to look at the Gaussian or wall distribution. And there are two parameters, mu and lambda. Mu is just mean in this inverse Gaussian. And lambda is a kind of dispersion parameter to tell you how dispersed the distribution is. So mu hat is just going to be the sample of your observations on y. And lambda hat is And we're going to, in the MathCAD worksheet that's attached to the same class of syllabus, I show how this is derived. And so we can derive lambda hat also from the sample moments.
What does y represent here?
That's the random variable. It has that distribution to wall. So then in the next one, y is also the random variable, and it's a gamma distribution that has two parameters, p and lambda. So the gamma distribution has as its special cases the chi-square and the exponential. Chi-square, we all know how to use that. The testing hypotheses using chi-square, Lagrange multiplier, likelihood ratio, and wall. So we know all about that. So this distribution is what is this. Exponential distributions can be used to model all kinds of things. The normal is an exponential. Special case of an exponential. So the question is, how do we implement our method of moments estimator? Well, we need to derive the moments. So the way to derive the moments is to start with the log likelihood, and we can differentiate with respect to the parameters and get the moments, and then solve the moments for the unknown parameters, and then go back and substitute away from the population moments by our sample moments. So the mean and the variance for our gamma distribution is p over lambda and p over lambda squared. So we can see that the first central moment and the second moment centered around the mean is p over lambda squared. And you can work backwards to get p and lambda. I have seen this example. We can also differentiate the log likelihood with respect to the other parameter p. And when we do that, one of the things, we get a new moment that we'll call the log of lambda and c of p. C is a very special function, mathematical function, and that's equal to something we'll call m hat star. We're going to come back to that in a minute. There's a book by Floria, Intermediate Statistics, in which he tells us what the moment generating function is, and we can differentiate the moment generating function with respect to t, its argument, in order to get the different moments. And so this is the moment generating function. We differentiate with respect to t, and so we can get the different moments for the random variable y, which has this gamma distribution. And so the rth moment is gamma times 1 over lambda raised to the r, gamma of t. Incidentally, what does the gamma function do? In discrete, when you operate on a discrete integer with the gamma, what does it do? Create factorials. So the gamma of 6 is 6 times 5 times 4 times 3 times 2 times 1. Of course, you can use continuous arguments in the gamma as well. So if we set r equal to -1, then the -1 moment is equal to lambda over p minus 1. So now before we had two different ways of getting the estimates of the parameters, and now we have a third. We have a third moment that we can use. We used m1, we used m2, and now we have this thing called m minus 1. Well, I guess we had 3 before. So now we have m star, so we can solve, we have an equation that has m star as a function of lambda and p. We have m minus 1 as a function of lambda and p, and we also had m1 and m2 before. So now we have 4 different moments that we derive, and we have only 2 unknowns. So this is an instance where the method of moments results in an over-identified model, because we have too many ways to get the 2 unknowns. So this is a drawback to the method of moments. Some models are over-identified. For something like a normal, that doesn't happen. So in your textbook, there's some data, and using Green's data, the estimates of the different sample moments are there in the square brackets, and you can pick any pair of them to solve for p and lambda, and of course you're not always going to get the same answer. That's what statistics is all about, and that's what the story about over-identification is about.